Hello everyone. This is our second lecture for Chapter 11, Two Samples Hypothesis Testing. In this lecture video, we will discuss related samples design and related samples hypothesis testing. This t-test is not as complicated as independent samples t-test from the last video. In our last video, we introduced a hypothesis test for situations when we observe independent samples. An independent sample is one where different participants are observed one time in each group. So we collect one observation or score per participant. We can select two independent samples in one of two ways. We can select a sample from two different populations, or we can select a sample from a single population and randomly assign participants to two groups or conditions, as was described in the previous video. In this video, we describe a hypothesis test for when we observe related samples, samples where participants are observed in more than one treatment or matched on common characteristics. So we're collecting two observations or scores per participant. So in independent samples, we're collecting one observation per participant. In related samples, we're collecting two observations or scores per participant. There are two types of research designs commonly used to select related samples: the repeated measures or related samples design and the matched subjects or paired subjects design. These designs are analyzed in the same way. However, the data are collected differently for each. The most common design is the repeated measures design or within subjects design. In this design, each participant is observed twice, once in each treatment. We can create repeated measures by using a pre-post design or a within subjects design. Using the pre-post design, we measure a dependent variable for participants observed before, pre, and after, post, a treatment. For example, we can measure athletic performance, that's the dependent variable, in a sample of athletes before and after a training camp. We can compare the difference in athletic performance before and after the camp. This type of repeated measures design is limited to observing participants two times, before and after a treatment. Using a within subjects design, we observe participants across many treatments, but not necessarily before and after a treatment. For two samples, let's say we want to study the effects of exercise on memory. We can select a sample of participants and have them take a memory test after completing an anaerobic exercise, and again after completing an aerobic exercise. In this example, we observe participants twice, but not necessarily before and after a treatment. Anytime the same participants are observed in each group, either pre-post or within subjects, we are using the repeated measures design to observe related samples. Here are some more examples for repeated measures designs. 1. Are reaction times different with dominant hand versus non-dominant hand? 2. Are wait times at amusement park rides reduced after implementation of new loading-unloading procedure? 3. Does BMI or body mass index decrease after bypass surgery? The matched subjects or matched pairs design is also used to study related samples. In this design, participants are selected and then matched experimentally or naturally based on common characteristics or traits. The matched subjects design is limited to observing two groups, where pairs of participants are matched. In a matched subjects design, different but matched participants are observed in each treatment, and scores from each matched pair of participants are compared. We can obtain matched pairs in one of two ways: experimental manipulation or natural occurrence. Matching through experimental manipulation is typical for research studies where the researcher manipulates the traits or characteristics on which participants are matched. We can match pairs of participants on any number of variables, including their level of intelligence, personality type, eating habits, level of education, and/or sleep patterns. We could measure these characteristics and then match participants. For example, we could measure level of education and then match the two participants with the highest level of education, the two participants with the next highest level of education, and so on. Matching through natural occurrence is typical for quasi-experiments, where participants are matched based on pre-existing traits. Pre-existing traits are typically biological in nature. For example, we could match participants based on genetics, like biological twins, or family affiliation, like brothers, sisters, or cousins. Each trait or characteristic is inherent to the participant. There is no need to measure this in order to pair participants. Pairs of identical twins or brothers, for example, are paired together naturally. Here are more examples of matched subjects designs. 1. A researcher wants to know if mean length of stay in for-profit hospitals is different from mean length of stay in non-profit hospitals. They randomly select 20 individuals in for-profit hospital and match them with 20 individuals in non-profit hospital by a diagnosis. 2. A prison warden wants to know if men receive longer sentences for crimes than women. They randomly sample 30 men and matches them with 30 women by type of crime committed and records their lengths of sentence. The related samples hypothesis test follows the same 4-step procedure we outlined in Chapter 9 and in our previous video on independent samples. So step 1, state hypotheses. For related samples t-test, the null hypothesis states that there is no mean difference. On this slide, I've provided the hypotheses for upper-tailed tests, lower-tailed tests, and two-tailed tests. Step 2, set the criteria. Select the alpha level. In our class, this will always be given to you. Locate the critical region. The t-critical values for the t-statistic are obtained using degrees of freedom, alpha, and whether the test is a one-tailed or two-tailed test. The degrees of freedom for related samples t-test are the same as degrees of freedom for one sample t-test. Degrees of freedom equals n minus 1, where n represents the number of difference scores. Related samples t-statistic is structurally the same as a one-sample t-statistic from Chapter 10. Related samples t-statistic is based on difference scores d, instead of raw scores x, or sample means m. So to prepare for statistical analyses, we need to calculate difference scores, or the difference between first and second scores. Difference scores are d equal to x2 minus x1. our analyses will be based on these difference scores, ignoring before and after data or paired scores. We calculate a mean of difference scores by adding the difference scores and dividing by n, where n represents the number of difference scores. Hopefully you recognize these formulas' structure. Variance and sum of squares are calculated in the same way. All we are doing is substituting x, the raw scores, for d, difference scores. This should all be very familiar to you by now. Step 3. Calculate related samples t statistic. Here is the formula for related samples. This should also look somewhat familiar, as it resembles the one sample t statistic formula. The related samples t statistic formula is structured as follows. Sample mean of difference scores minus hypothesized population mean of difference scores divided by estimated standard error. Based on the null, the hypothesized population mean of difference scores is always equal to 0, so we can simplify the numerator. We just have the sample mean of difference scores divided by estimated standard error. The numerator measures the actual difference between sample mean of difference scores MD and the population mean of difference scores μD. The denominator measures the expected difference between sample mean of difference scores and population mean of difference scores if the null is true. Estimated standard error of difference scores gives us this expected difference. For related samples t statistic formula, estimated standard error is calculated as the square root of the sample variance of the difference scores, divided by sample size n, where n is the number of pairs or number of difference scores, or sample standard deviation of difference scores divided by the square root of n. Step 4, make the decision. To make a decision, we compare the obtained or calculated t statistic to the t critical value. We reject the null hypothesis if the obtained value exceeds the critical value. If we reject the null, we must provide a measure of effect size. Effect size for related samples t is measured in the same way that we measured effect size for one sample t in Chapter 10. Specifically, you can calculate an estimated Cohen's d, or you can calculate r squared to get the percentage of variability in a dependent variable explained by the independent variable or by the treatment effect. When estimated Cohen's d is used with related samples t-test, we place the mean of the difference scores in the numerator and the sample standard deviation of the difference scores in the denominator. Another measure of effect size is the proportion of variance or variability in a dependent variable that's explained by the independent variable or the treatment. Percentage of variability is calculated using the same formula used for one sample and independent samples t-test. Effect size can also be calculated using confidence intervals. Same as we did for one sample t-test in Chapter 10. We find the interval estimate reported as a confidence interval and state it within a given level of confidence, which is the likelihood that an interval contains an unknown population mean. Using mean of difference scores, we calculate the confidence interval by adding and subtracting a margin of error, which is obtained by multiplying t critical value and estimated standard error. The advantages of related samples design, or repeated measures design, is that it requires fewer participants, especially if we are observing pre-post. We are able to study participant changes over time. Related samples designs reduce or eliminate individual differences since we're using the same participants, which leads to substantially less variability in scores. The disadvantages of related samples design are as follows. There may be factors other than the treatment that causes participants' scores to change during the time between measurements. Participants in first treatment or participation in the first treatment may influence score in the second treatment. This is what we call order effects. Counterbalancing is a way to control time-related or order effects. One last slide for related samples t-tests. The assumptions that must be met in order for us to conduct a related samples hypothesis test are independence of observations within each treatment condition and normal population distribution of different scores. I will post a video to demonstrate how to conduct an independent samples and a related samples hypothesis test.